Alright, so let's get started. Today we're going to do chapter number 4 on threads. This will be painless. It's actually a pretty easy slide set because we already talked about processes last time, if you remember, if you were here. The concept of threads, very similar in concept, but threads and processes, believe it or not, are implemented differently on operating systems. A process is any running program in memory. So when you double click on a program and you run it in an operating system, it gets created in the form of a process, and process space gets created, and the program instructions get run, and then the program goes and finishes, and then it gets taken out of memory. And so you can think of the process space as a memory abstraction. And in some operating systems, we have multiple threads that are mapped to one process, or we have one thread mapped to one process, and a thread is the thread of execution. It's the, that doesn't really define it, it's the executing program. It's the mapping of the memory, very similar to a process. There's a lot of overlap in concept, because if you only have one thread mapped to one process, then what we're really talking about is either a thread or a process. It's kind of simultaneous. Some people used to think that threads were considered lightweight processes. They used to be called lightweight processes for years, because you can open up a thread inside of another process, and then another thread inside of another process, and they're all shared the same memory space. But in this particular case, modern day operating systems, it's really a one-to-one mapping. So what we're going to look at today is the mapping that takes place, the overview of what threads are, the multi-threaded models, threading issues, Pthreads, and Windows XP threads. Look at Linux and Java threads as well, because they're all implemented differently, which is interesting. So the process is just the generic concept. Everything is a process. And the threads is where we get some interesting differences between different operating systems. And here's a single versus a multi-threaded process. As I remembered, if you remember just a few minutes ago, I said threads are normally mapped to processes. So this here is one thread. On the left, a single-threaded process, where we have one thread that gets loaded in for this one single process. And then on the right-hand side, we have 3 threads. 3 threads that are multi-threaded. So it's multi-threaded because we have multiple lines. We have 3 in this particular case. Threads of execution happening for that one single process. And some people at this point are going, well, what do we care about any of this stuff? And what does that really mean? Well, if all processes, going back to what I said about the CPU a couple weeks ago, they all share the CPU time, and they all get scheduled with a CPU schedule to run. If it's thread by thread, then everybody's going to get the same amount of time. If it's scheduled by a process, and if it's scheduled by threads and not processes, then this particular process, if you're scheduling the thread activity, is going to get 3 times as much processing time on the CPU than this one will. Because this only has a single thread, this has 3 threads that are mapped to one process. So if the abstraction is scheduling the threads, this process as a whole is going to get a higher priority CPU time. That's why we care. So we can create multi-threaded programs to basically spread the work out among the program, and then have faster execution of that program, theoretically, rather than having just one thread in the program, in this case here, and one process getting allocated, equal time as all the other processes in the system. And that's the only reason why we care about threads, actually. Most of modern day operating systems is taking this route, and we'll look at why this route kind of get a little confusing in time. And also in configuration. But if we look at this route, we've got the spaces that are allocated, and this is just memory that's being allocated. And you notice for this thread here, the multi-thread process, the slide makes it look like about the same size, and it probably is the same size because every process is going to be allocated the same amount of space. But these threads are sharing the code, the data, the files. They have their own registers, their own stacks, but they're sharing this stuff up on the top. So instead of having registers and stacks for one thread inside of one process, we have registers and stacks for all 3 threads. So they're actually kept separate so that they can basically perform their functionality independent of the other threads. And we still have our code, our data, and our files as part of the process space. So Benefits: responsiveness, as I mentioned before, resource sharing, economies of scale, utilization of the MP architectures. We can get more processing performed. We can take advantage of better CPU scheduling, multiple schedulers, multiple CPUs actually, if we can spread it all out in terms of the abstraction and divide the work out. So user threads. Thread management itself is done by user-level thread libraries, which are the Pthreads. So the first programming assignment for this course actually is to create a simple shell, and in the shell you're creating a thread. You create a thread by using fork. Fork basically from a process creates another process, a child process. So we have that parent-child relationship of the process. For the purposes of what you're doing, we have this. We have a one thread per one process. So when you create a thread, you're really creating a process. When you say pthread, fork, new child, you're creating another thread that's inside of here. The parent thread stops working, the child thread starts working, and it's all sharing the same process space. Other operating systems, the Linux environment, some of the older breeds of Linux had experimented for a while. I think it was the System V actually experimented for a while with multiple thread mapping, and we'll get into why that causes some problems in the next couple slides. But for the purposes of this class and for looking at the concept of threads and when you create a thread in your program, I think it's just one thread running at one time, and only one thread really does run at one time inside of each process these days. Makes the mapping easier, makes it so that the memory can be organized, scheduled, managed centrally from a process abstraction. So there's three primary thread libraries: POSIX, Windows 32, and Java, as you could possibly imagine. POSIX is the Unix breed. And that's why I said before, Pthreads is the name of the library. This is what you're probably going to be using for that first assignment for this course. But you could use any of the other thread libraries if you wanted to. The Windows 32 thread library is not a default library that comes with every programming language on the Windows platform, because it's actually kind of difficult to create threads in a Windows environment. GCC and the Linux operating system supports the threading concept. You can fork a thread. There's a POSIX library, just basically it's a default added-in library. It's not something you have to add on top of it. The Win32 threads, you have to actually install a separate package or something to support thread libraries. Java threads, everything's a thread in Java. So whether you can actually create a thread. Every time you create a class and you run it, it just runs as a thread. So there's no thread library really for Java. Instead, there's synchronizing methods, synchronizing classes, working in the environment to essentially optimize the thread programming. In a Windows 32 environment, you're emulating the threads. So that's why that library is kind of iffy. If you want true thread programming, you work with the POSIX thread. This is the Unix environment. And the assignment that I gave you, that first assignment that we've actually gone over already, gives you an example using POSIX Pthread libraries for method calls for exec, for fork, and for some of the other things. Now these are user-level threads that I just talked about. In your programming, in your languages, you're creating a thread. You're doing it at a user level. The kernel also has a thread support because the kernel executes everything it's running in the form of a thread or in form of a process. So these are supported by the kernel. Example of this would be internal to the Windows XP 2000 system. It does actually use threads. Solaris, Linux, True Unix, True 64 Unix, well actually all Unix these days are supporting kernel level threads, and the Mac OS X actually does that too. You might be wondering, well, what in the world, how do I know the difference between kernel level threads and user level threads? If you're on a Windows system, the easiest thing to do is press Control Alternate Delete to go to the task manager. Look at running programs. Every one of those running programs is a thread. That's a kernel level thread executed by the operating system to set a print queue, to set your user interface, your desktop supports, your background services, all of the different features of Windows that runs. I would say really in the background, it's just running operating system features. They're all considered kernel threads. So we have the multi-threading model. And this is what I was saying before, going back to this other little picture. This is a 1-to-1, one thread mapped to one process. This is a 3-to-1, 3 threads mapped to one process. So the model looks like this. We either have a many-to-one, a 1-to-1, or a many-to-many. What does that mean? Is either have many. These are considered threads to processes. So, and we'll look at in a few minutes some of the different varieties. Let's talk about the many-to-one. Many user threads mapped to a single kernel thread. Example was that in the GNU Portable Threads library, the Solaris Green Threads library. Green because it was taking up less processing power, essentially. Here's what it looks like. We got 1, 2, 3, 4 different user threads mapped to one kernel thread, which means when the kernel picks this process up and looks at the abstraction of the thread itself, in terms of the execution, is an extension of all of these 4 that were created in the user mode. Because the user is the one who's creating the threads, and then when they create the threads, the mapping exists for a many-to-one. So kernel picks it up, treats it as one. That's where you get the faster processing, because those 4 could be doing different tasks for one program. So usually they are. We talk about multi-threaded programs. It's kind of like a multi-processing system. Multi-process, meaning more than one process running simultaneously, which is what Windows gave us, compared to DOS, which was one process at a time kind of system. Batch. DOS was actually referred to as a batched operating system in some ways because you ran command after command. With Windows, we have multi-processing. So are all those processes, within those processes, do we have user-level threads, and are they mapped to one single kernel thread, or are they mapped to multiple different kernel threads in terms of the abstraction? And this, by the way, is just an abstraction. You can't like take a snapshot picture of the computer at one time and say, look, here's the mapping. You can't see it. It's a level of abstraction that's applied to the concept. 1-to-one. This is where we have each user level thread mapped to a single kernel thread. Examples is what we have: Linux and Unix, all the current versions of Solaris, all of the previous versions of Solaris, and 9 and later. Well, 9 at the making of the slide set, it was up to 9. I should probably just take this out and just say Solaris. Windows, Linux, most of your general operating systems that you're familiar with, it does a 1-to-one mapping. What does a 1-to-one mapping look like? Here it is. One user thread is mapped to one kernel thread. Easy to keep track of the threads. Much easier configuration. Gives equal priority to all threads. In this type of situation, the kernel could take this one kernel thread that's mapped to these 4 and run it, and then skip another one. And if they were mapped equally, we'd have a little bit more control. So a lot of it's done for control purposes. And control, efficiency, abstraction, being able to deal with it without making a complex situation out of the scheduling. The many-to-many threads is kind of an interesting problem, and it's very hard to implement. Many different threads map to many different processes. Problem with that one is the overhead of keeping track to which thread is mapped to which process and keeping track of the execution time per thread. It really does create a more shared environment, but it's a nightmare to actually kind of implement. So the many-to-many model allows many user threads to be mapped to many different kernel threads, which allows the operating system to create a sufficient number of kernel threads. So Solaris prior to version 9, or some of the older versions of Solaris, not the most current ones, but the older ones, basically we're trying to run with a many-to-many model. Windows NT, the 2000 version, they had a thread fiber package that could be loaded on to add this support. What does it look like? It looks like this. Here's the many-to-many. Many user threads mapped to many different kernel threads. This guy might be going over here, it might be going over here. We don't know exactly how they're mapped, but the kernel is keeping track of this mapping. So these are the ones the kernel is running. This is what you get in the user mode. It's a little bit more complex in terms of how to divide out essential execution power. and fairness and efficiency and all sorts of other things. So you could have a situation where one thread gets stuck in a process that hasn't gotten any time yet, but all the other threads have finished already. So the program could essentially be waiting around for one thread to get some time, CPU time. So it could account for certain lags in program execution. But it's a great way of sharing the work, because here's what ends up happening in the long run. Every user thread has to turn into a kernel thread, because the kernel needs to know about the user thread, creates its level of abstraction for it, so they can process it, so it can schedule it on the CPU. How it schedules it, that's the interesting phenomenon we really haven't quite figured out yet, outside of a one-to-one mapping. Really haven't perfected it yet, which is why everything's pretty much gone simpler these days. We could go with a two-level model as an example, similar to the many-to-many, except that it allows the user threads to be bound to kernel threads, which basically says, all you guys have to go to this one, or you have to go to this one, or you have to go to this one. So it binds them all together, so it solves that problem of one thread, one lost thread. It's kind of like networks and packets. If one of the packets it's missing, the entire message is pretty much garbage, and it has to go wait for reassembly. It has to wait for all the packages to show up. So if you got a slow one, you got a delay or something, you've got issues. Well, what about the execution of programs? You have the same types of issues that might show up in that case. Some examples: the HP UX, some Unix Solaris 8 and earlier versions tried to do a two-level model. Keep in mind, these are earlier versions of Linux and Unix. Actually, just Unix, I'm sorry, not Linux, because this was pre-Linux days. This was in the Unix days. I believe, that HP UX still does two-level model of many-to-many thread mapping, actually, which makes it different. So if you've kind of wondered why some Linux versions like Solaris is different from IBM Linux versus HP Unix, excuse me as I keep saying, I should say Unix. The thread models are significantly different, so are the uses of processes, so is the CPU scheduler, so some of the other internals of the kernel itself. Here's a two-level model explaining that we have a user thread here that's mapped to a kernel thread, and then we have all these three mapped to these different ones. And we're basically saying that we can map, although we have multiple mapping, we're specifying the map. Essentially, we're able to bunch them together in kind of a multi-level, two-level approach. Threading issues. So let's say we're going to build an operating system, we're going to implement threading, whether we go with them many-to-many or one-to-one or whatever configuration we might want to work with. The semantics for it are generally in terms of a system call, as I mentioned in Chapter 1, actually, system call interface, in terms of a fork or an exec call. In your first assignment, you'll be forking a process and then running an exec, which are these two different system calls here. You're doing that because fork actually creates a thread. Fork actually creates a process. And a process is going to be a child process from the parent process. And inside of that child process, because the parent's going to wait, so you fork a child, the parent waits for the child to execute. Exec is actually a thread abstraction. It's not a full process. It's just going to, this is basically the same as this system call, except for it says, well, you know what, don't create a new process, create a lightweight thread, and run this program. And exec basically runs something. It runs a ls command, runs some sort of binary file that's out there, executes it, sends the control back to fork the child process. You don't actually have to fork and then run an exec. You could just run an exec off of the parent process if you wanted to. Which is why it's one of the reasons why they call threads lightweight processes, because in theory, they're not creating and not allocating the same level of resources as a process. When you run fork, you're actually creating process abstraction. You're adding something to the jobs, to the process list, to running processes. When you exec, you're not doing that. You don't get a number. Nobody waits. So. More issues may be associated with thread cancellation. How do you cancel? How do you stop a thread? Signal handling. How do you catch signals? How do the threads identify that a child has stopped or a parent has gone away or something? Thread pools, the configuration of that. I'm going to go through all these in a few minutes in a lot more detail. Thread specific data. and then scheduling or scheduler activations. So the semantics of fork in exec, does fork duplicate only the calling thread or all threads? It only actually duplicates the calling thread in most modern day implementation. If you think of the concept of the multi-mapping in HPUX, we've got multiple threads mapped to multiple processes. It's got to basically make a duplicate of all the threads that it's being forked inside of. So the child normally gets access to the parent's memory space, and if there's only one thread, it's only going to get that parent calling thread. If it belongs to a process for which it might actually share work among some of the other threads that are also mapped to that same process, then it might actually get all threads copied. But in theory, it's a copy of the calling thread and not all threads, which is one of the issues actually when you think about it in terms of implementing a many thread to one process mapping technique. It causes a situation where it's not really, you don't necessarily know what you're supposed to be copying when you create a child. In fact, the environment might be very dynamic, might be changing, it might be hard to actually implement something of that nature. Thread cancellation happens when a thread terminates, so terminating a thread before it is finished. How do you terminate the thread? It's another interesting, it's like, we know how to do it. We know how to terminate a process in DOS, Control-C. So, or close a window, which is basically doing a Control-C in a Windows environment. Two general approaches to thread cancellation from a programmatic point of view: the asynchronous cancellation and the deferred cancellation. Asynchronous terminates the target thread immediately. It just says, right now, you're done. The other approach, which doesn't leave as much garbage, that's a little bit nicer, is the deferred cancellation. That says, it allows the target thread to periodically check if it should be canceled. You can also create an an implementation where you say, when your job is done, you're canceled. So it's kind of like how when you shut down Windows, you can shut it down now, or you can wait until all the programs close and then shut it down. So, which is kind of synonymous with that. Signal handling, also mentioned in your first assignment, actually, and it's a sig signal for the interrupt, for the exit call or something. When the user presses Control-C, that's probably the easiest example to give you because it generates a signal. So what do we have? We have an interrupt comes from the keyboard hardware, comes through the kernel, gets turned into a signal that gets sent up to the user mode, and the user mode thread can catch it. And the user mode thread basically has to look for a signal handler to be watching for that signal. So if you press Control-C on your keyboard, that one actually gets sent up anyway, so that's not a good one. If you press Control, one of the function keys, something to print screen or something, there needs to be something to say, hey, that keyboard combination was hit. Go into, and then what the kernel does is it picks it up and says, oh, we have this activity coming from the hardware. Let's go look at our signal handler table, our vector table, where we've got all the codes with all of the human readable or user mode readable signals. And it's usually an SIG underscore something or a signal something, where we generate a name, sort of like a system call name, that we send back up to user mode and we catch it. So when we're doing thread programming, one of the things we can do is create a signal handler to essentially catch the signals and basically work synchronously with the user. So signals are used in Unix systems to notify a process that a particular event has occurred. In the process, in the fork call, it actually invokes a handler. So when you do a fork and the parent process waits, and on the wait method that's being run, there's a signal handler in there, and it's waiting for the termination of the child process, which is going to generate an exit signal. And it gets sent back to the parent. So all of the threads in the operating system are basically run through signals, and they catch signals and they send signals to each other, which is where we get the mutex and we get the signal support for in the kernel itself for user mode thread programming. So if you're going to do thread programming, you're going to use POSIX threads, and you're going to do it on a Unix environment or a Linux environment because we have kernel support for it. It's built right in. Not the same case in a Windows environment. You can't normally, unless you load on third-party libraries to do Windows threads, Win32 threads, you don't actually have the same facilities built in, and the same services are not being provided by the Windows kernel. So, signal handler, it's used to process signals, and signals generated from a particular event. The signal is delivered to a process. The signal is handled, which means that some event happens, essentially. So some options. You can deliver the signal to a thread to which the signal applies. And then you got to find out which thread does the signal apply to, which is kind of difficult, actually. You can deliver the signal to every thread in the process. If you have a multi-threaded map to one process, it makes it easy. You can send it to all the threads that belong to a process. Or you can deliver the signal to certain threads in the process, not all of them. Or assign a specific thread, let's just say thread, to receive all the signals for the processes. So in the theory of Windows and Unix modern day implementations, if we only have one thread per process, it's doing this one here. It's delivering it to every thread in the process. Why not just send it back up? Actually, you can build a signal handler outside of the process too. It sends it to all processes. In fact, it's kind of like setting up a flare gun. Who sees the flare that goes up in the sky? Everyone who's looking. So essentially, other processes could take over and interpret signals that are sent if you have a full broadcast type of environment. And again, this is a decision that operating systems designers make in terms of how efficient they're going to be. If you send it out to everybody, you're sending a lot more messages than if you find the right one who's supposed to be receiving this message and you just send it to him or her, the process. Then you end up with a little bit more efficiency, but it's slower. Because the purpose of the signal is to send up an immediate response that's generated. And you don't really want a delay in that. If you have a delay in that, it's not immediate anymore. So there's too much processing. And you certainly don't want the kernel sitting there trying to figure out which signal goes to which process. Which thread is this process inside of this process, and how is this supposed to be mapped? So another concept we have is called thread pools. A thread pool is you create a number of threads in a pool where they all wait for work. So instead of one thread, you map a pool of threads where you have multiple workers, multiple executions. Some advantages of that: usually slightly faster to service a request with an existing thread than create a new thread. Because you have a processing time for creating the thread. And not only that, but you've got the abstraction and the thread management that the kernel has to take care of. So if you have to actually create a new thread inside of your process to get something done, it's slower to create a thread, run something, kill the thread, create another thread, run something. So instead you start out with many different threads that are all mapped together as one thread, and you just switch to another thread if that's supported. So it allows the number of threads in an application to be bound to the size of the pool. So we actually have thread pools in a lot of different multi-threaded environments these days because it's easier. We can limit the number of threads. We can make it easy to switch between one. We can allocate a lot of work, essentially. So it kind of predetermines prior to runtime how many threads are going to be assigned. Assigns the threads. Calls it a pool. Pool belongs to a certain process, and then we go back to the one-to-one mapping. Instead of one thread, we have one thread pool that's mapped to each process, which is how you accomplish multi-threaded mapping to processes without having to worry about multi-threads. Create a pool of them, put them all together, assign them to the same group, take the group, send it over. So, thread-specific data, so that allows the thread to have its own copy of the data instead of sharing. And if we go back to this little picture I had over here of all the threads, they're all sharing the same data. Right at the beginning I had code data files. This would be, let's say it's a level of abstraction for each. This is the process memory space for your two processes. This is about the same. This in here is the code. This is when we double clicked on our program, we have the executable code that's translated into machine language. Gets loaded up. We have data, static data that's being created. for each one of the, integer I, that we create. I is equal to something or other, and we manipulate essentially the code using variable. This is our variable data, and any files that we have open are going to be mapped as well to the process. If you notice over here, the code, data, and file is exactly the same, which means all of these threads are sharing, which means they all belong to the same code or the same running program. Not accomplishing much outside of more execution power versus a single thread. We don't have to do this. This is a single mapping where all threads are mapped to the same process space. We can actually cut this out like we've done the registers and the stacks. We have to, in this particular example, separate out the registers and the stacks because this guy's running some of the code, this guy's running, some of the code, that guy's running some of the code. Can't put it all together. How do we know which thread belongs to which activation record? And I'm going to make a slight assumption that you realize or you know what the runtime environment looks like. Maybe. Are you guys familiar with the concept of the runtime environment? The abstraction of the runtime environment? If you don't understand that, you're not understanding what I'm saying in terms of code, data, and files, or in terms of what this is all about. So let me give you a 5-minute overview of what I call the runtime environment. Runtime environment. Well, when we have an exe file in Windows, most people can relate to this. We have a shortcut icon on the desktop. We got a program in a directory somewhere. When we double click on that, it enters into what's called the runtime environment. And the runtime environment is Microsoft. I'm just going to use a Microsoft Windows example here. Microsoft Windows, it's the operating system's way of controlling that running process that you just created. So you had a program that turned into a process. First thing the kernel does is put a new entry in the process control block and say, hey, we have a new program. Somebody clicked on, and let me just call it Notepad. Somebody clicked on Notepad. Okay. So it creates a new process space, and that's what you're looking at the slide here. And in the process space, it loads the code. And the code is that executable file. It's all the machine instructions that are inside of that. It loads a spot for data, a spot for stack. Actually, what's missing here is heap. There's heap memory actually in here as well. So this doesn't really represent the full runtime environment memory space, but it's fairly complete. Any open files. And then from the code, in order to run this process, it gets put into essentially the CPU scheduler. CPU scheduler takes and runs each one of the processes. Maybe just about 1 or 2 lines of code from each process, and then it puts it back into the process control block, pulls another process out, runs a little bit of that one. This is where we get multiprocessing. This is our multiprocessor that we're looking at. Because only one program at a time can run on that CPU. How does the program get run is controlled by what they call the runtime environment. The runtime environment is the program that runs the program. And the program that runs the program, called runtime, works on a stack architecture. Stack architecture is think of this like assembly language, if you've ever seen assembly language, or machine language. Well, machine language is really hard to understand, but assembly language a lot of people have seen. We've got line-by-line instruction. We load those on a stack. We load the stack up till it's semi-full, and this is basically configurable. The stack size is a runtime-specific kind of phenomena. We load the code up on the stack, and we pop off each instruction, and that's what the CPU scheduler is running. So it's allocating data space inside of the memory. It's allocating space for the stack. There's also a heap space for dynamically allocated memory that's not stack allocated. So the stack allocated memory generally goes into the data section of the process. If the process is going to open up any files, any external DLL files, anything that might have associated with it, it might use, again, some of the process space to store that information. But all of the instructions get loaded up on the stack. The stack pops them off and it executes them when it gets CPU time. Eventually the code is all done. After you've loaded it all up, popped it all off, you've executed the program, then this whole thing goes away and the program gets taken out of the exe process that was created, gets taken out of the process control block, and everything gets emptied out, memory gets, unallocated, and then we start the old process over again the next time you double click on something. So that's actually what's referred to as the runtime environment, and the memory that's associated, which is what you're looking at the slide. The memory that's associated with each process is configured either with multiple or single threads. The threads are the stacks. How many stacks are you going to have in there? Which means if I had a bucket of 100 items and I had 3 sub-buckets to put it in, I could fill up all 3 sub-buckets. If I only have 1 sub-bucket, and let's say each sub-bucket only holds 10 items, I'm not going to process as much. If I only have 1 10-bucket instead of 3 10-buckets, this has got 30% more processing, which means when I get CPU time, I've got more to run. I get run me, run me, run me. Everything gets run. So that's why it's more efficient, actually. And unfortunately, it causes issues in terms of the implementation. And it's very difficult, actually, to kind of configure correctly, because the abstraction is just a little bit deep. So. All right, so we were talking about threading pools, signal handling, actually, I think was where I was at. So going back to the signal handler as a concept, if the kernel catches a signal, it already knows everything in the process control block. It already knows what it's scheduling. It can send a signal back up to one of the running processes, or to one of the threads that belongs to the process, or to everybody. Simplest technique is actually just send it to everybody, and whoever's supposed to be catching it, catches it. If they don't catch it, they don't catch it. And then I think I talked about the thread pool already, actually, and the thread-specific data is where I was at, actually. So if you have thread-specific data, as we saw before, the data was shared by all 3 threads in that other example. So thread-specific data allows each thread to have its own copy of the data itself. This causes overhead. Instead of having just 1 copy of the data, now you got space allocated for 3 copies of the data in that particular example, rather than just sharing it. Plus, you don't have any synchronization between them. But if you share the data, then you got inter-process communication issues, multi-threaded deadlock, starvation, all sorts of different sub-thread issues that might go on in terms of that running process. But to share the data is useful for when, specific data is useful for when you don't want to have control over the thread creation process. When using a thread pool, you want the threads to think independently, then you can give them their own specific data. You could theoretically have 2 sets of data, one for the process and one for each one of the threads, but then the synchronization is going to be pretty hectic. So scheduler activations. So what are activations? You know those stack entries that I was talking about in the runtime environment? I'll give you my 5-minute review of what runtime means. Those are actually called activation records. So the scheduler deals with these activation records, or activations for short. And what are those? Those is just the, add A to B, take B, add it to C. Those are the instructions that the CPU is supposed to be, the brains of the operation, is supposed to be reading those instructions and processing them. So both many-to-many and 2-level models require communication to maintain the appropriate number of kernel threads allocated to the application. They need to communicate with each other so that they're not duplicating activation records, causing more work for themselves than actually needed. Schedule activations provide upcalls. An upcall is a communication mechanism for the threads in the thread library to call to themselves to synchronize their activations. Communication allows also an application to maintain correct number of kernel threads by basically allocating the scheduled activation records per thread. So, Pthreads, POSIX standard, API for thread creation and synchronization. If you're working in a Linux, Unix environment, the only way you can create a user-level thread is through use a POSIX library. There's actually a couple of other ones out there. There's just a lightweight thread C++ library out there as well. POSIX is probably the most popular and generally used because this is what the kernel is using. So it gives you full system call interface support to kernel thread creation. And there's an API. This is an API. Specifies the behavior of the thread library itself. Implementation is up to the development of the library. Certain POSIX implementations are slightly different. So you have different versions of the exec, different versions of activity or behaviors that occur when you run a fork. Depends on the platform, essentially. Common in Unix operating systems, Solaris, Linux, and also the Mac OS X. You can run Pthreads in a Mac program. So you could actually go to a terminal prompt on a MacBook, write a GCC program that uses threads, and create your own kernel level threads, essentially. You can't do that in Windows, however. Windows does support threads, but in a different way. It implements a one-to-one mapping, as I mentioned before. Each thread contains a thread ID, a register set, separate user, and kernel stacks, private data storage area. This is when I said before you can press Control, Alternate, Delete, go up to the task manager, and you can see all your running threads, all your running programs. It's because it's a one-to-one mapping, you can call a thread a process, because each thread is a process and vice versa. And so you can see all the processes. Actually, I think Windows calls them programs. So you can see which programs that Windows has started and which programs has each user started. And you can usually click on it and kill it. And that's about all you can do, really. See how much memory it's taking up. See how long it's been running. You can actually get at the thread ID, at the process ID. Whether or not it means anything, good point on that one. Register sets, that you probably can't get at. Separate user and kernel stacks. You can't really get at any of the private data storage either. You can basically just get a list of running processes, which would be equivalent to running jobs, JOBS, or running PS on a Linux system, and you're essentially bringing up the task manager. Not as much information. It's not a full-fledged program. It's just going to show you the output of a list of all running foreground and background processes that happen to be running on your system, which is why in that first assignment you're implementing something like that. In fact, you can just run PS, take the output, put it into an array or something, and show it to the user. You don't have to reinvent the wheel with that. The register sets, stacks, and private data area are known as the context of the thread. I actually call it the runtime memory, but it is the context of the memory that's associated with each one of the threads. Contains the stack, that's the data, files, heap, all that sort of information. Primary data structure of a thread includes is the execution thread block, the E thread, which is the code, the kernel thread block, the mapping to the kernel of created abstraction, and then the thread environment block, which is nothing more than abstractions for labels put on the memory that is being kept for each one of the threads. Linux threads refers to them as tasks rather than threads. Actually, you could call them jobs as well. We have task and job is pretty much the same synonymous word in most Linux implementations these days. They don't actually call them threads. Thread creation is done through a clone system call, or actually most people would load POSIX libraries in Linux and run POSIX actually. And so you're running fork instead of clone. But there is an equivalent Linux abstraction to be used from a programmer's point of view for system call interface that's supported with Linux. You're not going to get this interface on a Unix system, but you can take the Unix system and install it on the Linux system, which is kind of interesting. There's a lot of people that do thread programming. They want the thread libraries to be consistent. Why do you use clone to create a thread when you can use fork? And people get used to using certain syntax. So clone allows a child task to share the address space of a parent task or a process. It does the same thing as a fork does. It's just called clone. Java threads are managed by the Java virtual machine. You can't. There's no thread library. There's no system call interface. There's nothing. Java, the JVM, is an operating system in itself. It does its own thread management. The programmer in Java can't create a pointer, can't create a thread, can't create a lot of stuff, actually. But that's done because the JVM is doing it for the programmer. So threads may be created by extending thread class. So you have a hierarchy, and you have the thread class that you're extending, or implementing a runnable interface. Runnable interface also does that as well. You can don't even have to extend the thread class or implement the runnable interface. You can just use keywords like synchronize and stuff to actually invoke the Java thread synchronization methods, which is essentially turning a running class into a thread. Here's the Java thread states. So we have new, comes new, start, makes it runnable, and then it sits and waits. And then it finally exits when it's done. So this is pretty much the life cycle of a thread, is its transition from new to runnable. And then if it's blocked, it means it's running in an asynchronous fashion, which is what we have. So when we say synchronization, we say we know that these methods are running synchronously. Make them run asynchronous. So make them block for each other. So it's kind of interesting. It's kind of like the word synchronization you would think would say make them all run at the same time. Instead it says, well, synchronize their activities so they don't all start running at the same time, which is kind of interesting. So, and if you've compared it or looked at it, you'll see that the thread programming in Java is the simplest to accomplish. You don't like thread programming and you haven't taken a Unix course, don't like systems development, programming in Java, thread programming in Java, simple. Very easy. And if you'd like to do the assignments for this course in Java, you can do that. You don't have to take the C approach. If you really want to learn it, I'd take the C approach, actually. That was lecture number 4A. And 4A was on threads. 4B is kind of an interesting concept. In 4B, I'm just going to start it. I'm not going to go through the whole thing. Unless you're going, oh, did we already finish the lecture? Talks about the concept of inter-process communication, which I've actually kind of started talking about already. In terms of, and I'm going to go through the concept of inter-process communication today, and then next week we'll look at the classic IPC problems. And the classic IPC problems fall into only two separate categories. One is the concept of two threads blocking each other and causing a deadlock situation. And the deadlock situation occurs when neither one of the threads can run because they're both waiting on some shared resource. Or one of them grabs a resource and doesn't let it go, so the other process can't handle it. The other process can't grab it. Or we have a situation that causes starvation. Starvation is when one thread is holding on to a resource and none of the other threads can actually get to that resource because one thread is not going to let it go. It's like, well, when people, it's like starvation in the real world. Not giving any food to some threads. Eventually they're going to starve. But in the programming environment, they never die. They always stay around usually. And deadlock threads do not die either. So, and I would say, is this, kind of a trick question. And I've asked before on, actually I've asked this on midterm exams before. I don't think you guys have a midterm in this course. I don't know. So how many threads does it take to create a deadlock? The answer to that question is 2. You can't have a deadlock with only one thread. It doesn't work that way. But I have actually had, it was a multiple choice question. It said 0, 1, 2, most people hit 0 or 1. But you need 2 threads to create a deadlock. So what I'm going to do is kind of talk about inter-process communication, going through the classical IPC, which stands for inter-process communication problems. And the first one, and this is the theme of one of your next assignments, I believe it's assignment number 2, which is the producer-consumer problem. And as soon as I get done with producer-consumer, I want to take a look at assignment number 2, and I'll finish with that, because you probably should be working on 2 or 3 at this point. So what is a producer-consumer problem? It's when you have 2 threads running, and you have a shared buffer. So the buffer is shared, i.e. is a standard variable, perhaps. It's a value. It could be a memory address. Anything where you have something shared between 2 processes. You have a producer that produces, means it puts something into the buffer. And then you have a consumer that consumes, it takes something out of the buffer. So this buffer doesn't actually have to be a buffer, like a memory buffer. It can be a variable that is shared among 2 separate processes. And so here's some progress in time with the consumer and the producer. And the producer on the top, P1, is producing 1, producing 2, producing 3. It's going in here. And the consumer here is taking 1 out. So it's taking another out. It might be taking out 3 instead of 2. So the items in here keep getting changed. So when the items down here are being taken out, the values might be changed. It depends upon the timing between the 2 threads. So both processes are started at the same time. The consumer uses some old value initially. Then you've got some issues with non-synchronization between the 2, between the value of the buffer essentially. You also have situations where the consumer is trying to consume, but the producer hasn't produced anything yet. And where the consumer is blocking the producer. So it's standing there with the door open saying, hey, can you give me some stuff? But it's consuming all of the resources, so the producer can't produce anything, which is classic kind of problems that happen with that. And the situation is actually called a race condition. Whoever gets there first is going to grab it. So we synchronize the consumer and the producer to eliminate. We don't want race conditions. Race conditions are bad because the timing of which process starts first, so we make it normally so that the producer starts first and then the consumer starts second. So we can essentially eliminate that race condition, especially, and then also create this concept. And this concept that I'm alluding to is called mutual exclusion, where if the process isn't working on this, it's not holding on to it. And only one process at a time can actually go in here to get this information, to either write to it or to read from it. So the concept of the mutual exclusion creates the ability for the producer and the consumer to run simultaneously without having to set the producer to run first. Because if producer doesn't run first and consumer runs first, it goes in here, it holds on to the buffer mutually exclusive, which basically means mutual exclusion means only one person at a time can look at it or read it or write to it. It's mutually exclusive per process. So if consumer comes in and looks at it and it says it's empty, it should let it go. Go back and let the producer look at it and go, oh, it's empty. Here, let me produce something. And then if the producer hasn't done that yet, the consumer comes up, it's empty, it's empty, it's empty. Has to release it, essentially. So you don't actually have to set it, like hard set it so the producer goes first. It will eventually go first after the consumer has checked it multiple different times. So it's kind of like how kids go, are we there yet? Are we there yet? Are we there yet? That piece of code that's shared is actually called the critical section or critical region. And we create mutual exclusion to the critical region in terms of the classic scenario. The critical section is the section of code in which the processes accesses and modifies shared variables. So this is the critical section, and we create mutual exclusion to it. And this is just the terminology, because the terminology essentially is what usually throws everybody off. Shared variables. Anything that's shared. It can be a shared buffer, it can be a variable, it can be an array. Anything shared is really considered the critical section. It doesn't even have to be one piece of information. It could be an entire process, a function, a class, a method, or something. And then mutual exclusion, by definition, a method of preventing for ensuring that one of the specific number or a specific number of processes are in the critical section at one particular time. So only one person or one group of processes. So why processes need to communicate to synchronize their execution? Otherwise you've got one process running and then the next process running and then the next process running. Why bother? Why bother having a multi-threaded application if that's the case? If they're not all running at the same time, you might as well just have one run and the next one, and then you got batch processing going on. But we don't have that. And from an operating system's perspective, we build in interprocess communication from a kernel level so that the processes that are running can all share the memory properly and all can communicate and not corrupt each other's information or any of the critical data. We also need to exchange data back and forth, information. So, rules to form a critical section. So no two processes may be simultaneously inside of their critical section. So that's where we get that mutual exclusion from. No assumptions are made about the relative process speeds or the number of CPUs. This is CPU independent, actually. And it's also speed independent because it doesn't really matter how fast CPU is or what's going on. If two processes are trying to read a piece of or write a piece of data simultaneously, one of them is going to get the wrong read value. One of them is going to get the wrong write value. So a process outside of the critical section should not block other processes from going inside of the critical section, is another general rule. And then no process should wait forever. If you wait forever, that's where you get starvation. When you're deadlocked, it means another process is in there, and it won't let any more processes come in. So you're deadlocked. And then you're essentially starved when you have to wait and wait and wait. And while you're waiting, you're not doing any processing. You're just sitting there. So that's when you get those windows that says waiting. Those are starved windows. So here's our starvation. Just to reiterate that point, mutual exclusion problem, starvation. Indefinitely delaying the scheduling of a process in favor of other processes. So you never get a chance to run. It causes usually a bias in the system schedule policy. A bad scheduling algorithm could cause that, could cause starvation, especially if the process never gets an opportunity to run. The solution is to implement some form of aging queue. So then in scheduling, CPU scheduling, we usually have multi-level processing queues. So we have the short, the medium, and the long-term scheduling queues, where we put CPU-bound processes in one, IO-bound processes in another, and then we have the middle one that kind of works as a kind of an aging thing, where if it's been in long-term too long, it goes to the middle, or maybe it jumps directly to the short-term. And we have algorithms that run in the background that perform calculations to see how long has the process been waiting. Because what we're looking at in terms of optimizing the environment is to create a fast-running operating system, right? We want processes to run instantly. In order to get that, we have to see, well, if one's been waiting too long, we have to run it. So, which is where the aging comes in. It eliminates the concept of starvation, because if you've got an aging thing in there, you're going to block. You're going to preempt a process, put it back, and say, okay, you can't run anymore. It's like the traffic cop coming over and saying, okay, you guys go this way, you guys go this way. You have to fix traffic issues. The other problem of deadlocks, just to reiterate that point, is where you have two or more processes. It takes two or more processes that are blocked waiting for an event that will never occur because someone's not letting go of some resource or some event's never going to occur. So they just sit there and they wait indefinitely. It's like a situation of deadlock in the real world is when you have a one-way bridge and two cars approach, or you have a single lane bridge and only one car at a time can go across the bridge. And you have two cars that approach from both directions, and they both want to go on the bridge at the same time. They're not going to make it. They sit there and they wait for the other person to back down. Eventually one of them's going to back down, but in the meantime they're deadlocked because you can't go anywhere. You just sit there. But somebody has to go somewhere. So the solution to that problem is kill one of the processes. Make somebody move. So generally A waits for B to do something and B is waiting for A to do something. Both are not doing anything, so both events never actually occur, they're just waiting. So, in terms of how to implement the mutual exclusion concept, three possibilities. The application, you can do it from an application level. The programmer builds some sort of method into the program to create the mutual exclusion. You can actually implement this in hardware. So there's special hardware instructions provided to implement mutual exclusion. It depends on the architecture, and it depends on how sophisticated you're going to be in terms of providing hardware support. If you do it from a hardware level, it's a little faster than doing it from a software level. Software programs create overhead, and they're looking for deadlock, and they're looking for mutual exclusion. It's because you have something else running to detect this, or something else that you have implemented in there that's not really part of the execution of the program, it's just to prevent problems. So generally causes overhead. Or you can have the operating system do it, provide some services that can be used by the programmer. All schemes rely on some code for entering into the critical section and exiting out of the critical region to share it properly. Okay, this is where I said I'm going to kind of stop halfway. So somebody has to remind me, maybe the TA, that I stopped at mutual exclusion. I'll kind of review the concept of mutual exclusion at the beginning of next week's lecture. Because this basically goes into the producer and the consumer implementation. But I want to take a quick peek at the assignment number 2, just to refresh my memory before we go. I believe it is the reader-writer, the producer-consumer problem. It is, no, it's CPU scheduler. Okay. Well, we haven't gotten to that yet. If you look at assignment number 3, I believe, maybe for this course, let's take a look. One of them's copying a file, process synchronization, yes. So assignment number 3, you could possibly start working on. You want to create a console-based application that creates a couple of processes. And you have a producer and you have a consumer. If you have the textbook, you actually have the code for this already. Use any language that you want. The textbook's going to give it to you in C++. You can use Java if you want. Producer should open up an input file and repeatedly copy values into what's called the circular buffer. Circular buffer can be an array. It can be anything you want in terms of its concept or in terms of its implementation. Concept is you've got a producer who opens up a file, reads the contents, put it into a buffer. And then you have a consumer thread that writes a file, takes the contents out of the buffer and writes it to a file, and you're implementing a copy command. So you're copying one file to another file using two threads, because it's faster actually to do it that way. You're implementing a CP command is what you're doing, and you're synchronizing the thread activity so the producer doesn't waste any time producing if the buffer's full, and the producer can stop and let the consumer consume. So you can, the trick of making this efficient and fast is in the synchronization of the reading and the writing to that circular buffer. So you can go through and read the rest of the directions on your own, but that's the concept that you're implementing. You could probably do it in Java really easily, actually, because it has file I/O actually support really easy built into the language itself. So, and you're creating copy file, input, output file, and the N and the M is basically going to be the number of bytes, the size of the circular buffer, the specifications for that. So. And from what I understand, we're populating the LMS with the assignments. They're probably not in there yet, so you can still get them from bhacker.com if you want to start working on them. It is in the middle of October. We have till the end of November, so we've got a month and a half, I think, left on the term. Not a bad idea, which is why I'm talking about the assignments now. Not a bad idea to actually start working on these assignments. You've got 5 of them, I believe, total for the course, but let me just check my memory here. Memory's not so good lately. Let's see. Fall. Principles of operating systems. There's 5 assignments. We've already actually, number 3, number 1. Next time we're going to actually, pretty soon we're going to start talking about number 2, which is going to be CPU scheduling. That was actually pretty easy. Number 4 and number 5, I believe, are on memory management. Let me take a quick peek here, actually. Deadlock avoidance is number 4. Number 5, I believe, is a paper, but let me just check. Main memory, it's a paper. So you really only have 4 programming assignments, and one of them is a paper that you're writing on memory-related concepts. Because really the heart of operating systems is CPU scheduling, process control, and then scheduling of those processes, stuff like that, memory management. The features of an operating system, that is really secondary in terms of the core concept. The features would be the user interface, file support, stuff like that. So. Questions, comments, concerns about threads? That was all of chapter 3 and part of synchronization. I believe next time we're going to be hitting very quickly, we're going to be getting into CPU scheduling after threads. So next couple weeks. Okay, if you don't have any questions, we're all done for today. You may go sign the roster if you haven't signed in already.